All right, welcome back, everyone. This is lecture 5, and let me just. Okay, so today's lecture is about the practical aspects of how to train a neural network, how to implement. So we did talk about how to implement in terms of how it works, but today we'll be talking more from the perspective of what are the practical issues that we might face and how to deal with them. And we'll continue discussing that in the week that's coming up. Because if you remember what we said in the previous lecture was something like this. And let me just quickly summarize that. This. Okay, so I have an input text, right? So this is my data. And then it goes into some layer. That's like my first layer, right? That's what we termed this as. And so what happens is there is this Z, which was the sum, right? And then there was this activation, maybe I'm calling it A. So this is my layer 1, hidden layer 1, right? And then there could be multiple hidden layers. So let's say I have the second one. Again, so this was Z1, A1, and then Z2, A2, and then maybe Z3, A3, sorry, lowercase 3. And then finally, I'll get some predicted value. And that predicted value is essentially used for the loss, right? So loss is a function of y hat and y, right? And so this was my forward propagation, right? That's what we said. So this was my forward propagation step. Okay. So now what? Now we need to train my network because these are not the most ideal weights, because basically I started somewhere here and I would have initialized my W1 and then the W2s and the W3s, right? And then I got some output, but obviously these are not the best because this was just something that I used as an input. So I'll have to optimize this. And to optimize this, I use what? Yeah, exactly. So you use back propagation to propagate my gradients and then do the update in the gradient descent, right? So that's exactly what I'm going to do. So once I have this, I go back, right? And in every layer, there are some things that I need to calculate using the gradients that I have from here. So basically here, I'm going to begin with, if you remember, I'll have the dA, right? So I begin with the last layer, whatever it was, 3, right? Which was the differential of L with respect to A. A was my activation. And then I'll also have DZ, right? Using both of them, right? I will eventually in this layer here, I will compute using both of them. I will have the dW1, the gradient for, sorry, 3, the gradient for this one, and then the dB3, right? And so I keep going back, and in every step, my goal is to calculate this. dW2, dB2. And I will be using dA2, dZ2 here, right? So 4 equations in every back propagation step in every layer. Exactly 4 equations, right? And so I'm writing it in a vectorized form and then eventually here, right? So dW1. And if you remember the equations that we had last time, so there is this dA and dZ that I'm computing, and that has a recursive kind of a structure. So the exact equation is given in the paper that I pointed you all to. So you should be utilizing that. But I've given you a vectorized kind of a notation of how to eventually, sorry, this should be dB, right? How you should be estimating and doing your gradient descent update, right? But this is not all. This is more like a theoretical kind of explanation of what's going on, but now you have to actually go and implement it. Now, the good news is that most of the deep learning frameworks that we are using have some built-in ways of dealing with these gradients. So most likely the homework that's coming up today, you will not have to go and manually do something to compute these values. There are ways of doing that. For example, if you're using TensorFlow, there are ways of getting the gradients within a data structure and then utilizing it, right? So there are ways of doing it, but this is something that you should understand what's going under the hood, right? So that's something that's what's happening. Of course, you'll be using packages, and that's absolutely fine. But I need you to know that this is what's going on. Okay, and of course, just remember that these are matrices. Just a reminder, right? These are no more like vectors because this is not just like a single input, like all the inputs connected to multiple nodes here. And so this is a matrix instead of like a single row vector or a column vector. All right. So this is something that we discussed last time, and this is like putting everything together. This step was back propagation, right? Or back prop in short. And of course, you'll have to run multiple iterations of this to get the final weights that you're looking for. Okay. So now just by looking at this, you must be thinking that there are so many variables in terms of like the hyperparameters. I know that we are estimating my parameters, my weights, right, and my bias using this entire technique of forward propagation and backward propagation. But what about like these number of layers? Remember last time I said, let's look at a 2-layer network. Today I'm showing you a 3-layer network. And then we are not quite clear as to like how many nodes are there in every network, right? So all of those are variables there. And so we, in addition to this process of estimating the gradients and doing the computation for Z and A, in addition to that, we also need to understand how do these impact my overall output, whether it impacts or not, first of all. And if it does, what should I be doing based on the problem that I'm solving? So all of those are covered in today's lecture. Let's go back to the lecture notes. So today I'm going to talk about train, test, dev sets. We haven't explicitly talked about it. I know I've seen in many of your projects you were already familiar with the train test logic and why we do that. And so again, I still wanted to cover that in today's lecture. So I'm going to talk about that. We're going to like cover bias variance again, but now we also want to know how can we figure whether my project, like whatever you're working on, whether it's like a biased output or not, or whether it's like having high variance or not, and how can you do that, right? So obviously there is no formula for getting a bias or a variance. There is no like, unfortunately, we don't have an exact formula to get it. We know that my entire like error or my loss is made up of bias and variance and some irreducible error. But how do we gauge somehow that this has a high bias or my model has a high variance or both, right? So there are ways to kind of understand that. And then we'll talk a little bit about hyperparameters. I have a whole lecture on like hyperparameter and other things related to that, but still I'll introduce that today as well. Problem of overfitting, it's huge in neural networks, and you can just tell why, because we are like almost exploring every possibility. You think about it, like the fully connected network, right? So I'm trying to model like almost every possibility. So there is like a higher likelihood that my model is going to overfit, right? So that, and then finally, I'll talk about regularization and a few other techniques that help us combat this problem of overfitting. So we have ways to deal with that. And the most famous and the most commonly used like technique is regularization. So we're going to like dig deeper into that. All right, so let's begin. As I said earlier, like any project that you're working on, and this is your second one that you're going to submit today, you must have like figured already that there are so many variables in addition to just like the data and the model, right? And there has to be some kind of a roadmap that should be available to you so that maybe like high level you can follow it. Of course, there will be some like nuances in that in there, but there has to be a high level roadmap for that, right? So think about like applied machine learning is an iterative process, believe it or not. So even like, and specifically like when you are trying to implement a neural network, because there are so many variables involved, because there are so many configuration steps involved, there is this like notion of that first you'll just go and think about the problem that you're going to solve. Then you think about like what model you'll be using, and then you train your model on that. But then you might not be getting the results that you want to get. And then you'll have to iterate over certain things to improvise on that. So that's the general idea. Right? So here is a list of like all the things, all the input parameters that can be tuned, like fine-tuned or initialized. For example, how many number of layers should I have in my network? Right? Because until now, I haven't clarified how that like, if you think about the way we are like doing the computation, the more the better. I mean, the deeper the network, the more I can learn the underlying function, right? And so like what, like how much more is more? Like maybe I can go on and on, but how much? because like there is this trade-off of efficiency, because like training takes time and resources, right? So like what computer you're using, how much data you have, how much time you have, right? Well, believe it or not, like in my PhD thesis, I was running this. So we had this data set that we got from Amazon, and I used to run it for like 2 different algorithms, and one would take like days to finish on my like home computer. But I'm just like giving you an idea of like that was such a waste of time, because I'm just like, for those like one set of results, I'm waiting for like 2 to 3 days, and then I can come up with a conclusion. Okay, this is bad, and so let me go and run 3 days again. So that that entire process was painful, to say the least. So those kind of issues are there. So I cannot just like have infinite number of layers and I just like keep running, right? So that's that. And then the second is the number of nodes. So remember in the 2-layer network, we saw that in the second layer, I decided, let me have like 4 nodes, and then let me have 2 nodes and one eventually, right? So then the number of weights are in some ways related to the number of nodes, because you have that matrix of weights that you'll be estimating. And so for each of those, you will be calculating the gradient, right? And so that impacts the efficiency as well. So again, we have to decide, do we want all those weights? Do we want all those nodes? And when do we want all those nodes or all those weights? Okay, learning rate. So we have seen some of it even with logistic regression. So learning rate is that eta, remember in the gradient descent algorithm? So learning rates, of course, it's a good practice to use a variable learning rate, right? And there are methods to implement that as well. But in some problems, like a very simple problem, using a fixed learning rate works just fine. So like, again, there's a trade-off there. Activation functions, choice of activation functions is extremely important. Now, we've been talking about sigmoid, and the other one that we talked about was tan H. So sometimes tan H like takes a very long time to converge, right? So there are issues with that. And so like people have improvised, and now we have the ReLU that's like more popular with neural networks. And again, the choice of activation function is a part of the iterative process that I'm talking about, right? And initialization, so what weights should we initialize our model with? Remember, with neural networks, never initialize with zeros, unlike you were doing in logistic regression, because you're going to fall in the trap of symmetry. And that's something that we don't want in a neural, that's the whole point of like doing a neural network, right? I want to learn something more complex than what my logistic regression is telling me. So all of those things. And in addition to all of this, like there are certain data considerations as well that we should consider when we are planning a machine learning project. Okay, so I will like flip all these topics. Like, of course, I have them in like certain order. But I'm going to begin with the data considerations first, right? So as I said, like machine learning in general is like an iterative process. And in every project that you'll be doing in this course, I'll be asking you to pick your own problem. So that means you will come up with your own idea first, right? So this is the problem that you want to solve. And then you get the data, code it up, run a few results, run a few experiments, and get the results, right? So if you think about it, it's more like this cyclic kind of a process. So what I can do is you have an idea, right? So you have this idea, and then you have the data plus code, and then you run some experiments, right? To get some final results, but then you analyze those results, and then you see that these results are not quite what you were thinking, or like maybe the accuracy is low, maybe they're not doing a good prediction, they're not, the model is not doing a good job as you expected. And so you iterate through these 3 steps again and again. So one thing might be that maybe the idea can include the problem and like what models you'll be using. So maybe the models that you selected were not quite, they don't fit with the the problem that you're looking at, right? So if, let's say you were solving you needed a linear like regression type model, and you use some other model because the problem because you thought that the other model is going to do better, but it did not. So that kind of a thing. So this is like a whole, I would say, a process wherein you'll keep fine tuning things, right? And how do like different aspects of a neural network fall into place in these 3 or fit into these 3 categories? So that's something that we're going to see today. Okay, so as I said, the iterative process involves fitting different configuration of the models until we get the best results, meaning, okay, you've decided you're going to use a neural network, but like what configuration of the neural network? Meaning how many layers, how many nodes in every layer, what activation functions, and other things, right? So that's part of that iterative process. And then, like, of course, after getting the first set of results, you can fine tune it, you can update it, and then get another set of results until you arrive at what you're trying to do, right? So the data we are working with, like, it impacts the iterative process and the final results, right? And the current practice that like everybody follows, and I know many of you are familiar with that, with this process, is that you should be splitting that, like whatever data you have, that's all you have, right? So most likely you're working with a public data set, right? So you pick that up and you're trying to fit a model to that. So the way you should be doing that, and I've like outlined that here, but I'd still like to like, okay, so then let's say you have this data, right? The way you should be utilizing this is that this is all you have, right? And with this, you will have to fit a model, right? And then not just that, you'll also have to do something with the generalization part. That means how is this model that you fit on this data going to work with unseen data? But the issue that like we have is that this is all I have, right? Which is why I need to split it into a test and a train, right? Set. So what we do is like we have a training set, and I think we should be like following this going forward for all neural network implementations. So you'll have a training set, and then you should have a dev set, and then you'll have a test set. So let's think about what is test set. Test set signifies, or it like represents, I would say, the unseen data, the thing that's out there in the universe where my model should like be doing the predictions. So I don't touch that ever, not even in my iterative process that I just talked about. Because if I do that, then I'm biasing my model in some ways, right? So I don't touch that, right? Now dev is the one where like, first of all, I'm going to train my model, right, and get some results, right? And then I'm going to test on the dev set. That's also known as the validation set sometimes. And if I don't get good results, and we'll see like what good results can be, like where your model lies and what you should be doing and all of that, then you go back and then maybe make some updates in the configuration of your neural network, right? Make some changes. And then again, train the network, right? And then come back and check with this dev set again, right? Until you feel, based on your problem, whatever problem you're working with, until you feel that you have reasonable results. So once you have your reasonable results, then only you should be getting the final test results, which actually talk about generalization, right? So this actually generalizes your model because now you're considering your test set as something that's like out there in the universe. And this is what the prediction power of your model is for that unseen data. Okay. So this is what this section talks about. Train your model on the training set, validate on the dev set, also sometimes referred to as the holdout set, and repeat this process to get a good idea of the performance of your models with different model configurations. Okay. And once you have the best model, and then of course, this is subjective. What do you mean by a best model? Depends on the problem, depends on the data, depends on also some domain knowledge, right? And then the test set is going to get an unbiased estimate of your final model. So basically with the test set, you are like getting some estimate of how your model is going to perform on the actual data out there. Okay. So this overall process is like everybody's okay with that, right? Okay. So the next thing that we should be thinking about is that what size, like what is a typical size for a training set and for a test set and for a validation set, right? So if we think about like traditional machine learning, the way we used to split it, like the data set, was like by percentage. So let's say I have like this entire data set. I'm going to do a 70, 20, 10 split percentage wise, right? So I'm going to get like 70% in my training as my training data, right? And then 20% as my dev or validation set, right? And then 10 as the test. So this is what this is telling you, right? So that's how you should be splitting it in the traditional machine learning era, essentially. But now we have a lot of data, right? We have a lot of data. And it is like very common to be working with, let's say, like a million size data set, right? And if you think about the million size data set, and the whole point why neural networks are so popular now is because we have that data. And because we can extract so much information from that data, right? So if you think about like a million size data set, and then you just like hold out 30% in like your dev and your training, you're actually like just not utilizing a huge chunk of your data, right? And so the chances are that you're not extracting all the information from that like huge data set. And if you think about it, like if I did, instead of 70, 20, 90, if I did like a 98, 1% and 1% split in like a huge, humongous data set, in that 1%, I'm still getting 10,000 something around that, right? 10,000 values. So that's sufficient for validation and test, right? So that's what here I'm talking about. So based on like a lot of experimental evidence, so there is no like theoretical evidence for this that, okay, this is the best size for a train or a test, but like experimentally speaking, this is the split that you should be doing if you have like a huge data set, right? So 98-1-1 is the common, like, if you go and read the research papers, that's what they're doing, because 10,000 is good enough for your validation and then also for your test, right? So that's what this section talks about, right? So with the advent of big data and the fact that like deep learning algorithms work well with large data sets, we should be splitting the train, dev, test in by like 98-1-1. And then even sometimes in some problems, you can have this kind of a range as well. So that's like even more than 98. So you can go to like 99% and then 0.5, 0.5 for your test, depending on the data like set size. Because like if it's like a 2-3 million data size that you're using, then this makes sense, right? 99.5, 0.5. 0.5 will encompass like a huge chunk already. So that's that. Okay, so these are the data considerations, and going forward, like following this roadmap is something that I'm like suggesting everybody, especially when you start working with like deep neural networks. So these are some of the data considerations. All right. Okay, yeah, this is important also like from the statistical perspective. So the first thing, the most important aspect of like getting the data actually is that your train, dev, and test set must come from the same distribution. So from your knowledge of statistics, you can just like at once realize why this is the case, because you cannot get data from like some other source and then make prediction for something else, right? So for example, if let's say I was sampling, I was trying to predict who's going to win the presidential elections in the US, and I'm collecting data in Australia, so that's not going to work. Like obviously my prediction is going to be biased, right? So that's the like fundamental idea here. So that your train, dev, and test set must come from the same distribution. So make sure that you're like picking everything from like where your predictions need to be made. It's the same population essentially. So you'll have a sample, but then make sure that this model and these parameters and these like whatever you estimated, they work for that population only. They don't work for some other population. Otherwise, you're going to get biased results. Yeah, that's the first thing. And then here, I think we talked a little bit about it, but just to like reiterate this, dev set should be large enough to like rank the models, because I'm going to rank my models in terms of performance now. Because I have all the like, I have the ability to just like go and train any model and then compare it using this validation set, right? So it should be large enough to give you an unbiased performance measure of your model. Although we said that we don't want to waste a lot of my data in the dev set, I want it to be used in the training set, right? But then make sure that it does not fall below this like 1,000 or some like threshold value, because then it doesn't really make sense. Its results don't really make sense if it's like too small, right? So like maybe think about like, okay, be greedy, but not too greedy, right? So just like stop somewhere there. Okay. Another like very important aspect, like when you do this test, train, dev split, and then you make predictions, make sure that like once you've done everything, you've made changes to your configuration, you have selected the final model, and you have some results from your validation, and then now you're doing your predictions using the test set, and then reporting the results, like the error or whatever, right? Accuracy or whatever. Once you get your test results, you should not go back and like fine tune your model again. And can anybody think why we shouldn't be doing that? Why is it so dangerous? Yes. Exactly. So like it's like you're biasing your model, right? And so then whatever results you're reporting, you just like you actually went ahead and looked at the test set, right? And the fundamental idea of any machine learning problem is that you shouldn't be looking at your test set or where you'll be predicting, right? Your algorithm shouldn't have any idea or shouldn't get any information from where you'll be predicting. Otherwise, it'll get biased. So that's the reason we never touch the test set until we are done, and then we make our final predictions and conclusion on the test set and say that this is my model. This is the best it can generalize. Okay, so this is an important consideration. Please make sure that you follow that and don't like bias your model after looking at the test results. All right, so that was about data collection and usage and data considerations. So going forward, for every machine learning project that you're doing, make sure that you are considering these steps and then going forward accordingly. All right, any questions, doubts before we move on? This is pretty straightforward. I think like directly or indirectly we have talked about it, but today I just like wanted to formally about this again. Okay, so now I'll be talking a little bit about bias variance. And because this question has come up multiple times, even while you were doing your homework, I've got this question multiple times, like how do we understand whether my model is biased or it has a high variance, right? And this is an important consideration, I would say, and like including that in your analysis is always a good idea, right? So just let me quickly review what like bias and variance were. And just by looking at this graph, and we've seen this graph before, but still, let me write it down. Okay, so there is like my general error. Let's say it's the mean squared error for the most simplest possible scenario, regression, right? And this mean squared error is actually made up of like three components, like the bias squared. And you can see like any statistic textbook, it'll just like split the error up and it'll show you that this is the bias squared component and this is the variance component and this is the irreducible part, right? So I'm not going and doing that because I think you must have seen that before, plus some irreducible error, which we cannot do anything about, or noise, right? So what's happening is, and like instead of model training, I would like to call it like complexity, because the more complex your model is, this is the direction of like complexity increasing, right? And this is the direction of like error increasing. So here, if like your model lies somewhere here, right? And like you can see, this is the bias and this is the variance. So if you just like stop somewhere here, very simple model, right? You didn't use a lot of data and you used a very few parameters and you just stopped there, then maybe it's good that your model did not like overfit or overlearn, but it is highly likely that your model underlearned. That means it is like way away from the actual model, the actual function that you're trying to learn. So there is going to be a huge bias in this region, right? So it's biased from the actual function. It's away from the actual function. So the bias component of your overall error is going to be huge, right? Now, let's say I saw that this is like high bias region and underfitting is happening. So let me just go and like increase the complexity, just keep going. For example, in a neural network, just keep adding layers, right? Who's stopping me? So I just keep doing that and I somehow end up in this region, right? And this region, as you can see, is the region of high variance. So of course, I've tried to fit every possible intricacy in my data because I tried to learn each and every point, right? But in that process, maybe I tried to learn noise as well because I'm trying to fit to like every possible point. And so that's okay. Maybe I reduced bias to as much like as possible, but then I introduced a high variance. That means when I'm going to like, it's sensitive to every point. So my model is sensitive to every point. And so that's why there is a high variability in my model. And that explains like high variance, right? And so the issue with this high variance, this is like the biggest challenge in any this region here. And you can see the general error is actually a trade-off between both of them. But this is a huge challenge in like any deep learning, I would say, neural network implementation, this variance. Why? Because you've seen that those are complex models. So I'm trying to learn every possible intricacy, right? And so I'm going to end up here. And we're going to talk about that more later, but let's go back to the data when we split the data into training, test, and dev. And utilizing that, can we like gauge like somewhere like ballpark where my model lies, whether my model lies in this region, or because based on that, I'm going to like implement some solution, right? So a short answer to that is yes, you can. Okay, so here this was showing what underfitting is. So just like notice that curve here, right? If you look at the data, the curve is like way off, like it's not really fitting or doing anything as such, right? And so this is like almost like this is the best accuracy, and overfitting, like going and selecting every point, right? So then you can see the variability. Okay. So I don't know if you have tried reading some research papers in like related to deep learning, and I'll be pointing you to those as well. But you'll see there is a like less discussion of like bias variance for a lot of reasons, and especially the trade-off. But I think as machine learning practitioners, as people who are like working with data, we should keep that in our mind whenever we are like trying to fit a model and doing some predictions. So that's why I have a few examples to kind of give you an idea. And so by the way, these examples are not like exhaustive, because these numbers are not applicable to like every problem that you're solving or every data set that you're working with. But this should give you some idea of like, you will be fine tuning your models a lot. So how to configure, where to look for the issue. Okay. So let's say we are solving a binary classification problem, like a 0 and a 1, right? So let me write it down. So let's say I'm trying to like figure out a 0 and a 1, and like I fit some, let's say, logistic regression, neural network, I don't know, some model on my data. And I have on my training set now, to be more precise, right? And I get a 1% accurate like error. So that's like excellent, right? I almost fit everything except like some 1%. And then my dev set error is 12% using the same model, right? So what can you make out of this? Like, what exactly did I do here? Is it like just by looking at those percentages? Yeah, and why? Because exactly. So it did give you some high level idea what's happening. You cannot exactly tell like this was the value of the variance or this was the value of the bias, but just by looking at this, because the whole point here for using the training set was this is the model that you fit, right? And so you got the parameters from there, and then this is where you actually tested it, right? And so it's not generalizing. And the moment you know that it's not generalizing as well, right, it indicates overfitting to some extent. So now, of course, like we can argue here that in some problems, maybe this is okay. In most problems, it's not, right? So maybe some domain knowledge helps. But if it's such, I would like still say like from personal experience, if the difference is so huge, like 1 and 12, if it was like 1 and 5, then I would say, okay, it's not that bad, right? It's okay. But 1 in 12 is huge. So maybe going back and checking and seeing where it's overfitting or why it's overfitting, maybe we used a too complex model. So going back and doing like reconfiguring that, right? So maybe I used 5 layers. So let me drop 1 layer because maybe I'm learning too much from the data, that kind of a thing. Okay. If like there's this scenario where you have like the training set error that's 15% and dev set error 16%, right? So both are like pretty close to one another. But if for some reason from my domain knowledge, I know that this can be reduced, right? 15% is huge. For example, for like image classification where or image recognition, where you're just like recognizing whether this is a flower or not type problem, I know that this is huge. Like you can do way better than this. So that's like what domain knowledge means, right? So then this shows that the model is not even learning from the data that I've provided it. So then it's too simple. Maybe it's underfitting somewhere. Of course, it's generalizing well. It's like, but I haven't done anything. So maybe it applies to every data set out there, right? So again, it is indicating something. There is no like mathematical proof to show that this is what's happening. But these are the indications that you can just like see and go back and reconfigure your model. Okay. And then if you get a training set error of 15% and then a dev set error of 30%, then this is a case of both high bias and high variance in a problem like, as I said, image classification or image recognition, right? Where you were like having a binary classification problem. This is a flower or not. Because this is like a huge error for that problem. And then when I'm trying to test it to an unknown data, right, it's giving me 30%. So it has both high bias and high variance. And that is also an issue with like many deep learning algorithms, right? So that's telling you that. And then there is this training set error, very small, dev set error again small. So, oops, I think I have this wrong. This is not high bias and high variance, right? So if you have training set error that's really low, right? So you have learned well. And then the dev set error is also low. So then you're generalizing also well, right? And so this is like low, like this is not, the ideal model, right? This is the best that you can get. However, like again, these numbers are just like made up numbers. So again, it depends on the problem that you're solving, right? So maybe looking back at some papers, if that problem has been solved somewhere else and like what were the numbers they were getting and whether you're close to that or not also helps, right? So in most of the problems, like some baseline values for these accuracies are available these days. So I don't think that's going to be an issue. But then if you get something like really like some drastic numbers like this one, 15 and 30, then you just know that this is a bad model. There was no need to like then have that model in the very first place, right? 15% is bad by all standards for a binary classification problem. All right. Okay. Yeah, so, and there is another, so I have provided a link for Bayes error. So basically in statistics, there's something that's known as Bayes error that is kind of defining that this is the best that you can do, right? So you cannot go like, no algorithm can do better than this. So this is the minimum. So sometimes people compare like the performance against like the Bayes error. So I provided a link. I'm not going into the details of that. It's more of a statistical factor. But I just wanted everybody to know that like everything is being compared against that. Okay, so yeah. Okay, so like how should you, and because you'll be like implementing a neural network in the homework that's coming up today. So here is a roadmap. This is how you should be like going forward with your project. So begin with like the train, test, validation split, right? And then fit a model on your training, like training set. And then if the training error is high, right? So it points to the fact that the model has high bias, right? And so one way to handle that is like maybe choose a bigger network because you will be working with a neural network. So I'm like talking in terms of that. So maybe you're underfitting, right? So let's go and like make my model more complex. Let me add more layers or maybe more nodes somewhere, right? And or train for a longer period of time because you decide like how many iterations you want. So maybe you're not training enough. You're stopping before you should have, right? So that's that. And then maybe like repeat the step until you get like a reasonable error on the training set. Okay, so once like you have figured that this is the best you can do in terms of training error, given all the considerations of like how long your algorithm is taking to converge and how long you're running your everything, right? You have established that this training error is low, right? So once you establish that, then you should look at the dev set performance. Now, right? So once you have like, if you see the dev set like error is high, right? Although the training error is low, right? Then this points to high variance. We just saw. So my model is not generalizing well. And so now I need to do something about that. So if it's not generalizing well and it was doing well on the training set, what does that like point us to? If it's not generalizing well, that means it was overfitting on my training, right? So yeah, I know like a lot of information there that just like makes, that's why I've like tried to summarize, and this is something that you can just like follow blindly when you're working with your project, right? So then, of course, like how to deal with that. My model was overfitting. So one remedy is regularization. Of course, like another way is get more data and see like, okay, how does it fit with the other like more data added to the input or the training. But that's almost impossible to get because you just have your data set and you're done. Like you're not collecting data at any point, right? So if that's the situation, then obviously we have some tools to deal with it. For example, regularization. So you can apply regularization. You can apply other techniques, as we'll see some more of those today. And then once you're done with these two steps, just iterate over these two steps until you get like a reasonable low bias and variance. So this should be your roadmap given like any problem, any machine learning project. This is the high level roadmap that you should follow. All right. So yeah, I have provided links as well, so you can go and like read more about this. All right. Any questions, doubts before we move on? Okay. I know today's lecture is like more around like theory, and I'm not introducing any new models, so it's not as exciting. But trust me, this is going to be the most important. Like some of these concepts are going to be the most important part of your like any project that you work on. So that's why these are important considerations, like in designing your project. All right, so let's start talking about the problem of overfitting and why this is like so important when we talk about neural networks. So here is a research paper that actually talks about why neural networks are like known as universal approximators. And in fact, here they give a mathematical proof that even like as simple neural network as a single hidden layer neural network that just had one single hidden layer, it can approximate almost any function. So that's what this paper talks about. Very popular, famous paper that like in the machine learning community. This was, I think one of the earlier ones that came up with like how the performance of neural networks in general, right? So of course, we are not going to cover that in this class. If you're interested, you can go and check like how they provide the proof for why they are universal approximators. And all of that is good, excellent. But then that comes with some negative things as well. So if it can approximate like any function given some data, then I'm not like, so that means in some ways it is overfitting because it's like getting each and every intricacy out of that training set, right? So earlier, like what happened was that there was like this lack of data availability, right? And that led to poor performance. So before the advent of like neural networks, there was like more I would say literature on how to like lower the bias, how to get better models. But now it seems we have better models. And so these are such good models that they can like approximate anything. And so now I have another issue that's high variance, problem of overfitting, and now I have to deal with that, right? So yeah, so there are like methods to deal with overfitting. And one of the most popular ones, of course, I think you must have come across this is regularization. Right. And I'm going to give you some mathematical side of this as well, because I think that is important, although we don't go into too much math in this course, but I think that's important to understand. So talking about regularization, the general idea is that overfitting is caused by too many parameters and too much data as well, right? So basically more complex models, right? They lead to overfitting in some ways. Why? Because the more complex the model is, I am picking up every possible aspect of the data, and then I'm fitting my model in that data. Because like I'm adding more parameters to my data, right? So the more the complexity, like as my complexity increases, and you can just like tell by looking at this, my complexity is increasing here on the x-axis, right? And so I'm here in this region, high variance, and so I'm like overfitting. So one way to counter that is like, how about I just go and constrain the learning parameters or the weight matrices in my neural network? Because the whole point is that like I have learned every possible weight. So how about I just don't learn every possible weight? How about I just like explicitly make some of them zero? I can, right? And so if I explicitly make them zero, then I simplified my model to a certain extent, but I still let it like learn a huge part of like my data. But still, I just like explicitly went ahead and reduced the number of parameters, reducing the complexity. And as a result, I made my model simpler. And so that will reduce its tendency to overfit. And like it is going to generalize well. So this way of like explicitly going and making those parameters zero is known as like a hard constraint type model, right? So you can apply that. Specifically, if you've ever come across like polynomial regression type model, so there is like this practice that we can like go ahead and make some of the parameters 0, right? And so then that generalizes better than like learning every higher order polynomial, right? However, like there is another approach which reduces overfitting, and we use that. And specifically with neural networks, we use that, and that's known as like a soft constraint approach, wherein we are not like making the weights explicitly 0, but we are making it like making them really small so that their like significance in some ways is less. So we make like some of the features less important as compared to others, right? I'm still learning from the data, so I'm not missing out much information, but I'm explicitly like stopping the learning part somewhere by introducing something in my learning algorithm. And so that's the fundamental idea of regularization. Okay, so I've given a lot of like math here, but I would definitely like to, let me do this, write this here. Maybe I can write it here. Right, I think we have enough space. Okay, so the best way to kind of visualize regularization is with linear regression. Why? Because the loss is a quadratic function, and so we can visualize it in a two-dimensional kind of space. But the same thing applies to any other model. Of course, like we cannot, in some cases, we cannot have a proper quadratic loss function, but then we can have the approximate loss function that approximate a quadratic function. So the same theory, the same ideas apply, right? So I'm going to like just give you a high level idea of what's going on. So in like general, I'm trying to minimize my loss, and this is a linear regression model, right? And what I'm doing is like this was my, right? So this was my cost function, y hat y. So this was like something that I was like, sorry, minus squared, right? Because this is linear regression. So like predicted minus the actual squared, generally speaking. And like maybe in more like a weight type notation or a vector notation, I can write it like this, right? So this is what I'm trying to minimize in any regression type model. And you know that there is like the pseudo inverse algorithm that can analytically give me the exact solution for this, right? So I can solve that for linear regression. And so that is given by, and so let me just write it down. So let's say the weights for that. And this is a very well-known result. You can find it in any like regression textbook or any like linear algebra textbook. So this is the result that I get. This is a known result, right? So basically what I'm trying to say is that if I minimize the loss for linear regression, that's the results that I get, right? And I can solve it. All right. So what we're doing in like regularization is that we're saying that we don't want to solve it for the reasons of like overfitting, right? We don't want to solve it to the end. We don't want to get these results, but rather we just want to constrain it at some point. And the way we want to constrain it is that like my optimization problem under regularization like becomes something like this. So I'm trying to minimize my loss, right? And of course, minimize overweights subject to something that I explicitly go ahead and like make this, sorry. Okay, so this C here is like some budget that I specify, right? And what I'm doing here is that I'm like explicitly saying that of course I'm going to learn, of course I'm going to solve this minimization problem and maybe get somewhere close to this, right? But then my weights cannot go beyond this budget, right? So I explicitly introduce this budget constraint just to constrain my model from overfitting. So that's the fundamental idea that's going on in regularization. So basically I'm like regularizing like my overall learning process. Okay, so if you just think about this optimization problem, right? If I'm trying to solve this one, there could be like multiple cases. One case could be that let's say I solved this unconstrained problem, only this minimization, right? And I found those weights that were actually following this. So maybe I found this thing that was actually less than C. So that's excellent. I'm done, right? But what happens if I solve this like unconstrained minimization problem, this line here, right? Just don't think about the constraint for some time. So I solve that this optimization problem, right? And I found these weights, these linear weights that were greater than this budget. Quite a possibility, right? But then I said that I have to do something about it so that I can get within my budget, because I want to regularize and somehow make these weights small enough so that I am able to deal with the overfitting problem, right? So one good way of like visualizing this, and it's given in this paper here, and I don't want to draw it because like my drawing is bad, so I'll just show you, and then that is okay. Yeah, here it is. So of course I can write on it. So now notice what's happening. So this thing here, here, these are the weights from my unconstrained minimization problem, right? And these contours are the error. And this is a quadratic function in linear regression because it's a nice quadratic function, so we can visualize it, right? So now what I'm doing is I found this optimal point, but then I gave some budget, remember, and I wanted, let's say the budget was C. So if you think about like in two-dimensional space, this thing is like almost equivalent to like saying this W square in some ways, right? And so what I'm doing is, and let's say I said this has to be like less than C. So basically somewhere here it has to be like square root of C or something, right? So this is a circle, and I have like this thing as like square root of C. So basically what I'm saying is that if I have weight somewhere within the circle or within the sphere, then I'm good. I want my weight somewhere there. However, the unconstrained problem is giving me my weights here. So obviously I'll have to go and expand my contours, and I have to like iteratively get some other weights that bring me closer and closer to my feasible set. So this is like my feasible set, right? I need something within this. I cannot take this, right? Everybody is like okay with this idea, right? So I just like try to increase this error surface. I keep on increasing until I hit this like feasible set, because this is the best of both worlds. This is the best I can do, because if I keep like um, going and going, right, and so then I'm increasing my error a lot, so I don't want that as well. So this is the best of both worlds, like, so I'll get something here, right? And so at this point, like what actually happens is that remember the derivative of like loss with respect to the weights. So I'm just like, let me denote it by this, I don't know, dw or something, or maybe dw, right? So this will be like somewhere like dw, and the weights will point like exactly in the opposite direction at this point. So that's my like perfect place where I want my weights to be. Okay, so based on like some mathematical criteria, which is like the optimality condition at this point, I get this equation. And let me just like not go into the details. Basically, at this point, I can say that the gradient of the weights is directly proportional to the negative of the change in the weights. So I can like establish that, right? So this is the condition for optimality, basically. Again, I'm not going into too much details, but just to give you a high level idea of where that equation of regularization came from. So instead of like in like to get rid of this proportionality, I can come up with an equality, right? So what I do is I come up with this equality thing, minus 2 times lambda c and weights. Okay, so where did that 2 come from? 2 is only for mathematical convenience. We'll see why. It's like some constant, and you'll see why that is there. This lambda c, also known as the, I think, regularization constant or the regularizer in some different text. I'll just go back to the lecture notes and see what we are calling it. For like right now, from the mathematical perspective, know that this is like a Lagrangian's multiplier, right? So you're to get that equality thing. That's all that we're doing. And so if we just like write this equation at something like this, lambda CW equals 0, right? Now, if you think about this part here, right? And remember this thing, the weights that had the constraint, right? So if you try to like differentiate this, you try to find the gradient of this, right? So basically you'll get something like 2W, right? So this thing actually is a gradient of something like this, right? This is the gradient of this. And this is already the gradient of the weights. right? I already wrote that like dw, right? So basically what I'm saying is that the gradient of the weights plus the gradient of like this thing 2 lambda c uh, w transpose w should be 0. This is my necessary optimality condition, right? In other words, I can say that I should be minimizing this then. So basically minimize the loss plus lambda c w transpose w. Because whenever I'm trying to minimize, I'm trying to find the gradient set it equal to 0. So I'm like flipping that thing, right? So until now, what I've been doing is like all my life, I said minimize this L, but now I'm saying no, don't just minimize this L, but minimize this thing as well, right? So there are two advantages to like doing all this derivation, although you could have solved the original optimization problem, but the advantage is that this is more like an unconstrained optimization problem that's easier to solve, right? And also this gives us an idea of the fact that my error is actually an augmented error now, right? So it has this augmented term here that wasn't there in the original derivation. Okay, so all of that math is good as long as you understand the high level idea of like where we are coming from, right? We are trying to have some weights that are as close to 0 as possible, but also keep in mind that my error, like these error contours are not going huge because then my error is also becoming big, right? So I'm trying to find the best of both worlds. So now this type of like so this is like, this equation is known as the regularization equation because I'm trying to regularize my weights in some ways. And this is also known as the L2 regularization. Why? Because like I'm using this W transpose W, right? So the norm of the weights. And this is like the most commonly used regularizer, L2 norm. But however, I also wanted to talk about L1 regularizer. So I'll just give you a high level idea of what that does. Okay, so L1 is like, I'm not taking the square, but I'm just like taking the absolute value of the weights, right? So if instead of like, if we are thinking about the same scenario as this, right? So instead of these circles, I'll have something like this, right? Because I have this thing as my feasible set, right? So this is also known as like ridge regression or lasso. Sometimes you must have come across that term. Now, the only difference between this one and my L2 regularization is that if I hit these points somehow with my error surface, I can get exactly like the weights equal to 0, right? So that's one thing that happens here. That's the only fundamental difference. And then, of course, it depends on like what problem you're solving. My recommendation for neural networks is that try using this L squared. That's the practice. And yeah, like for now, that's okay if you understand that. But this is just like additional information I wanted to give, right? So there are other regularizers available as well. Okay, so all of this is good. But if we go back here, here, right? So this is what this section talks about. So essentially, now I have this in terms of like the most simple model, right? This was my original loss. But now you know I have something like this equation here. Okay, this equation here that I'm going to minimize from now on if I'm trying to use regularization. So there this is like this regularization term that had this like Lagrangian multiplier lambda, right? This thing, and then the norm of the weights. And then it's divided by like this 2 is for mathematical convenience, but this n is signifying the number of like your data points that you have, right? And okay, so let's like think about what's happening here. So if I say go and minimize this, the question arises, why is this helping me? How is this helping me? Well, if I'm trying to minimize this, earlier I was just trying to minimize this. So I was trying some weights that will give me the minimum loss. But now I have this penalty here on that and some input parameter lambda. So think of this lambda as some tuning parameter because you can explicitly say, okay, go ahead and penalize my model this much. So if this is high, then you can just say that I quickly have to like stop somewhere, like I have to stop quicker with smaller weights because I cannot keep like penalizing a lot. But and also think about like if lambda is 0, think about it in that way. So then no regularization and I am just like back to my original model, right? So this is like a penalty that you've added to your, like when you're trying to minimize your rates. So that's why this works. Okay. So of course, okay, this section talks about why we have the two. That's, I'm not even like touching that. Yeah, and so this is known as the regularization constant. Yeah, this is known as regularization constant, the lambda, and it's a hyperparameter. It has to be non-negative. In most cases, we take a very small value. We'll talk about hyperparameter tuning and then what values we can get started with. But usually, like a smaller value is okay. Depends on like how much you want to penalize your model. All right, so that's that. Okay, I think I've given you enough information. Let's like break for 5 minutes and then come back. If that's okay with everyone. All right, I think let's begin. There isn't a lot that remains after this. Like, I really want, like, the key takeaway from today's lecture should be regularization, because like, try and understand why this is happening and how you should be implementing in your models, right? Okay, so we talked about L1 norm and L2 norm, and now the question arises, how will we be using it in our like models, right? And remember, when you're like learning, you're like in back propagation, when you're learning the weights or the parameters, when your model is learning, essentially it's the gradient descent that's making like the weight updates. Okay, so here, like, I have specified what exactly needs to go into the gradient descent update. So instead of saying like the weight in layer L equals the weight in layer L minus the learning rate times dw, this is what we've been doing until now for any layer L. And by the way, this is going, these are the matrices, right? So just a reminder. So the entire matrices plus this regularization constant lambda over n times this weight. Okay, so let's quickly see what's going on here and why this is helping us regularize. So if you look at this update rule on the right-hand side, right, this is like L minus eta dw L minus this lambda over n weight L, right? And just look at these like weight terms. So essentially like this weight L is multiplied by this like 1 minus lambda over n factor, right? So I'm like somehow reducing my weight by this factor here, right? So my weight is decaying based on this factor at like every iteration. So that's why this like L2 regularization is sometimes also known as like the weight decay, because like my weight is decaying in like every successive iteration, right? So this is the only thing that changes in your gradient descent now. Now you have like, because remember I'm like having this augmented error now. And so based on that, like everything changes, and specifically this thing here changes. Another thing like this W square, like the norm for a neural network will be a matrix. And this is also known as the Frobenius norm. So if you come across that, do not get like overwhelmed with like, what is this Frobenius? Sounds something strange. So that's like the name for like this norm. Okay, so I have this link to this chapter on regularization for deep learning. So it essentially talks about the same concepts that I talked, like that I went through with linear regression, except that it's talking in terms of like deep neural network. This is something that you can refer to when you actually start implementing your models and when you actually start working with your project, if you want to like use regularization, right? So conceptually, this will give you a good idea of like how this is happening in a neural network. But like high level, just remember that what you're minimizing is no more just that loss, but some augmented loss. And you're somehow using that augmented term penalizing your weights. And so you're like explicitly making your model learn less, right? Because there is that weight decay that gets added. So this is an excellent read. I would say just like high level read it. It doesn't use a lot of math. So if you're like getting scared with the math part, this does not like go, of course, like they're showing like different, I would say vectorized portions as well. And like, you can skip some part of this, but I think most of it is like pretty evident, like what we talked about in class. So it shouldn't be like that scary math type of paper, right? So this is something that I highly recommend before you actually start implementing regularization. So the link is provided here. Please go and like read it whenever you can. All right, so moving on, regularization is not the only way of dealing with overfitting in neural networks. So there are other ways as well. The other popular way is this dropout regularization. So remember, we have like this fully connected network. And so we have like these nodes that are connected to one another. And I'm passing my, like in my forward prop, I'm passing through every node. And then in my backward prop, I'm like passing my gradients through every node. So I can in some ways control that. Like, why am I doing that, right? So let me give you a visual of like what I'm talking about. So for instance, like let's say this was some hidden layer, right? And then this was again some hidden layer, and then that had like final something. And so I have like this fully connected, and this, and maybe there are like more connections. Maybe I'm missing out some, but like you understand what I mean, right? So what we can do here is that like we can like if you think of these nodes as some like gates through which you're passing your information, right? I can randomly select or choose some of these to just like not be there as part of my network, right? So maybe like I can have some kind of a random generator that will select some of these nodes. Let's say I have like I generate some random numbers. So let's say like zeros and ones. And so randomly, I thought this is 0, 1, 1. And so this is out of the network, right? And so then as I move forward for every layer, I can do the same. Sorry. So for this one, let's say this was 0, 1, 1. Like randomly, I chose which ones to just like not include. And then I can keep doing that, right? So think about like a lot of nodes will not be there in your overall learning net, like in your overall network. And so you are explicitly making some of these weights that you'll be learning here and the gradients as like 0, right? So this is in some ways regularizing your network, right? So this is known as dropout regularization, where you are just like randomly ignoring some nodes. Yes. No, so again, you can, that's a good question actually. So you can decide how many nodes you are like, so maybe you thought that I have to explicitly go and ignore these nodes, or maybe your random generator is going to decide I have to ignore these nodes. So it totally depends. Maybe your random generator said 0, 0, 1, so I'm going to drop 2 of them and then keep 1. And then there are so that question actually takes us to the next level of like dropout regularization. There are variations of that as well. And so this here talks about this a nice article talks about this, like how can we randomly drop nodes. So maybe you want to drop nodes, but then you want to keep this constraint that I don't want like all the nodes to go off in a certain layer, right? So this article talks about that. Okay, let me just close it. Okay, you can go and like quickly check that. So maybe you can keep this constraint that in this layer I don't want like less than 2, because like you want at least that much, right? So again, that's like a hyperparameter. That's something that you will be deciding, or maybe like your random number generator decides. Yes.
Why would you decide
So like you can definitely do that. So like if you decided that, let's say you don't want to have a layer at all, then you can just like discard that layer. So all of that comes in the hyperparameter tuning part. Yeah. So like you have all the ability to configure your network the way you would want, depending on the problem that you're solving. There is no like right and wrong. It totally depends on the results that you're going to get, and then reconfigure your model. Yeah. Okay, so that's that. The third thing, like, of course, there are other ways of regularizing, but I'm just like covering 3 different aspects of regularization. So the first one was L2 norm, and then we know what L1 norm is, right? And then dropout regularization, and finally early stopping. So in your gradient descent, you must have like noticed that even in logistic regression. So this is nothing new actually. And so what happens is that like gradient descent, you can make gradient descent end a few iterations earlier than usual. And so how do you decide when to make it like stop, right? So one way would be to use your validation set here, right? So of course, this is a highly iterative process, but like in many papers, you'll see this result. So what happens that, let's say this is your error, this here is your error, and these are the iterations of your gradient descent, right? And you're somehow like keeping a track of your training error and your validation error, right? So obviously, like as you train more and more, in most cases, like the training error is going to go somewhere like flat here as you increase the iterations, and then maybe you don't want to go beyond this, right? And then what happens to the validation error? Most likely it is expected to follow the similar kind of pattern. But in some cases, like when you have this problem of overfitting, you can at times see that this validation like is like having an inflection point. Not quite, but having an inflection point. So then maybe that kind of indicates that that's where you should be stopping, because then your algorithm is going to overfit in your training, in your test set as well. Right? So this is something that you can also do, like keep track of like, if these were the number of iterations, this is my training error. So this was like the train set, and this was like your validation set. So that's another use of validation. But this is where like my iterations should stop, like maybe wherever, sorry, my inflection happened. Because beyond that, most likely I'm going to overfit, right? So this is what this section actually talks about, early stopping. I think in this, and I don't think like, I know that this paper, the paper on regularization, has more details on like early stopping and dropout regularization as well. So again, when you're reading, you can get like more details of like how to best do that and how like mathematically speaking, they are helpful, both of them, to regularize your model. Okay. Any other questions before we move to the last part of today's lecture? And this last part, by the way, I'm going to like keep talking about it in the week that's coming up as well. So because I know that I've given a lot of information today, that I think you should take time to absorb that, and then like maybe we'll move forward. But still, let me give you a high level idea of like what hyperparameter tuning is and what hyperparameters are. So now, given that we know that our models are like my deep deep neural network is such a complex model, and you see that there are a lot of configurations that you need to do, like how many layers, how many nodes, uh, what should be my learning rate, right? All of those are like termed as hyperparameters. Why? Because I get to decide those. My learning algorithm is not going to learn that from my data. I'm deciding them. Those are my input parameters, and those are going to affect my results, right? So there is this huge, like, um, a huge chunk of your machine learning designing of your projects and then implementation of your project goes into hyperparameter tuning. And so that's why this is like so important, because this is like in some ways impacting your results. So the question arises like, are there any like ways of like which ones are more important than the other, or like how should we be selecting them? And there has to be some guideline on how we should be doing that. And so the short answer to that question is yes, we do have some guidelines. Of course, like no specific guideline that says, okay, do this. But then you have some guidelines just like you had with the data thing, right? Have this much percentage, or like look at this to gauge bias and variance. Similar to that, we have this here. So you can get like, first of all, you need to understand like which parameters are more important. And this paper here, this pointed to the source, it has like in some ways ranked them in order of importance. I would be very careful in saying that this parameter is more important than the other. It depends on the problem you're solving. It depends on the data you're using in a lot of ways. So of course, like there is this research paper and very well cited that tells like this is the order of importance. So I've just like taken that from there. And so it says like based on some experimental evidence that learning rate, the eta, is like the most important. And then if you're using any optimization algorithms, then comes these things like momentum, it's beta, remember, if you're using the momentum part, or if you're using RMS prop, then the beta 1 and 2 that were there, right? And the mini batch size, so they are like equal importance. And then number of hidden layers, learning rate decay, regularization constant lambda. And then, yeah, so these are like, this is some order, some way of thinking about it. Like, again, I would take it like with some caution, not necessarily like, I think in many cases, like maybe lambda could be more important than like the momentum or like the RMS prop parameters, right? So it depends, of course. All right, so once we've figured that these are the hyperparameters that we need to specify before we actually start training our model, right? So then what are some of the techniques for hyperparameter tuning? And how should we begin with that? What are the considerations that we should like keep in mind when we are like choosing a hyperparameter? And this is a very nice like source that talks about it. And I would focus only on one aspect of this, and you can like take all the time to read it. And okay, so I'll just skip this. And these are like some of the approaches for the tuning process. Again, like as I said, I'll take this with a pinch of salt, right? But these are like some high level processes that you can follow. So for example, the first one is like the first two are grid search and random search. So this here shows what grid search is, and this shows what random search is. So maybe I'll just like write down what this is saying. Okay, so let's say my hyperparameter one was the learning rate in my gradient descent, right? And then my other parameter was, I don't know, some epsilon. Remember in the Adams algorithm, the denominator had this epsilon, right? So I know that this epsilon is not very important, right? And this is grid search. Why? Because I have like some grid values. Just like notice why this is called grid search, right? So I have like these fixed values, and based on, let's say I picked up this eta, I'm going to pick this epsilon, and then do some like run some experiments with this value, and then come back and maybe like pick something else, and so on, right? So this is one way of picking these parameters. The only downside to this is, like, let's say this was a more important parameter and this was not a very important parameter. And so like what you'll do is that like we'll like keep picking different values of eta, and the sorry, like maybe we did this. So I picked like 5 different values, and because this wasn't like impacting a lot, I picked 5 different values for this epsilon and 1 for eta, and I don't see a lot of like change in my overall output because this wasn't as important. So those kind of like small corner cases can come up with this grid search, right? Because I haven't searched well enough, because I just like fixed these points, right? So which is why to like handle that problem, we have this random search, right? So I'm changing both with every new point, right? With every new point, I'm changing both the parameters randomly, selecting from this. There is another like variation of this random search that you just like focus on a smaller area with like more points, and pick like very small differences in the parameters. Why? Because maybe like a very small difference in your hyperparameter is changing your like output a lot, right? So then you just like want to confine your search. So of course, these are not the only ways of like how you can tune your hyperparameters or select your hyperparameters, but this is a starting point, and this just like tells you that there are ways of dealing with it. And as I said, I'm going to talk more about this, the lectures that are coming up. So today I just like give you a high level overview of like, there are like systematic ways of selecting like hyperparameters, right? So just like go through this article quickly. I don't think it talks a lot about other techniques. It mostly focuses on these two. Okay, there is another article. Okay, I think you can go over that. I think you wanted to go over this research paper. Okay, this is taking forever. Okay, so this one is an old like paper that talks about neural networks and bias variance trade-off. So why, like, we did, now we have a good idea of like how to ascertain like whether my model is high in bias or variance using my train test dev split, right? But this actually talks about like all the details in like in mathematical terms, right? And it like gives a good idea of like how can we mathematically speaking, where like our model falls when we are actually trying to decide whether this model has like a high bias or a high variance. So I think this again is like an important read for like those who are interested in the math side of things. But as far as like implementing your projects is concerned, like whatever we discussed in class, I think is sufficient. But if you're like just in case interested in the math side of things, that's why I like provide research papers as well to back that claim. Okay. All right, so that's that. Why wouldn't it let me go back? Okay, there is another research paper. Okay, so this is again talking about bias variance trade-off, also generalization. It will also talk about regularization. So it's like, I'm not saying that you have to go and read all these papers, but these are kind of a good backup whenever you are like kind of stuck in terms of like mathematically not able to like visualize things, right? So again, like going back to the regularization example that we did, you don't have to know the mathematical intricacies, but you have to know why we have the augmented error, and now we are trying to minimize that. So that at least that should be the key takeaway from that. All right, so I think that's all I have for today's lecture. Any questions, doubts about anything before we end? Okay, I think I've like given you enough information, so I'm sure it'll take time to absorb that. That's fine. Just like a quick announcement, so homework 3 will be released today, but it's not due in like a week. It's due in 2 weeks. So it's pretty open-ended if you just like go and read it. The first part actually asks you to do some research on certain things. So basically what I want you to do is like go and dig up some resources related to that problem. And that also has like some points to it, that the research part. And then you actually build the model. So there are like 2 important parts to that homework. And you have plenty of time to finish that, hopefully. So that's all I have for today's lecture. Thank you so much, everyone.